Thank you very much. I'd like to join all the other speakers to really thank the organizers for this wonderful conference taking place in this beautiful space. I also want to thank them for streaming the programs and making them all available online, which I think really has broadened the audience that can really participate, follow the proceedings. I mean, last night when I was taking a taxi cab from my home in New York to the airport to come here, even the cab driver was telling me about his ideas about how to take scattering amplitudes to 5 loops. So it was just, I got to the desk at the airport and the attendant was giving me her ideas about emergent space and gravity. I mean, it's just great that these ideas are having a worldwide effect. So really, thank you, organizers. So one thing that the streaming of the programs allowed me to do is follow some of the talks even though I wasn't here. And I noted that David, in his initial remarks, was recounting many of the questions that we've been asking for 20, 30, in fact, he told me at breakfast, 43 years, I guess, is the appropriate count for the age of string theory. And sometimes when you're dealing with real deep questions, of course, that's what you expect. It's going to take a long time to ultimately come upon the answers. But sometimes as well, if you're asking questions for a very long time and you're not getting answers, maybe it means you're asking the wrong question. And that, of course, is an approach that has been followed in recent years with regards to one of the questions that David was recounting, which is the question of what sets the vacuum state of string theory. And of course, there was a time when many of us believed, hoped that there'd be some mathematical directive that, say, would pick out one particular Calabi-Yau space, if that's the approach one wants to follow. That hasn't materialized, and of course, as we all know, that has motivated people to think of alternate scenarios. And of course, one of those scenarios is to envision this kind of a picture where we have many different, say, just to be concrete, Calabi-Yau compactifications. We imagine that perhaps in some sense they may all be real, may all be on equal footing from a theoretical standpoint. And then we can reframe the question of what chooses the vacuum state to a more cosmological question. Just imagine that you have a situation like this, but we allow for the possibilities that would happen in this context of tunnelings that would happen over timescales. And then the question of what chooses the vacuum state would really be a question of really understanding the detailed nature of these kinds of transitions, ultimately linking that understanding with, say, eternal inflation, if you will, to try to have a much more broad picture of what's really out there. But the question of what chooses the vacuum state, of course, would have a very different character in this kind of a setup. Now, of course, to be able to make this a picture that is more than just words, we need to really understand these kinds of processes in detail, really do calculations with them. And as I think we all know, in recent years, there's been, I'd say, the first steps in the direction of trying to understand in detail these kinds of processes. And what I'd like to do here in the brief time today is just recount some of the work that we've been doing in this direction. And all of what I'll be talking about was done with these collaborators, Pontus Alquist, David Kagan, Eugene Lim, Sasha Rangi, Yisheng Yang, and one of the papers is already in the archive, other one will appear shortly. So by way of outline of what I'll do in a little bit more detail, I'll begin with a pretty quick background discussion of some of the standard techniques that one needs for analysis of flux compactifications on 2B theories. Once we have that in place, we'll take a look at, say, the first step of the program, which would be to have some good understanding of where the vacua are in, say, some real concrete examples. Once we have those, then we can begin to think about tunneling transitions, and we can expand our perspective on this to not only consider vacua where there'd be tunneling, but also degenerate vacua, which actually will be where my focus will be when we look at some explicit calculations. And in those cases, rather than looking at tunneling transitions, we'll be looking at domain walls that connect two different vacua that will actually both be supersymmetric vacua in type 2b compactifications on a specific calabi-Yau. And here we'll find a little bit of a surprise in the detailed nature of the tunneling or domain wall solutions that come out when you actually solve these equations explicitly, as we will do. And then I'll finish up with some conclusions. Okay, now in Nadi's talk, he noted that it's always good to have one quick sentence that can summarize the main message of what it is that emerges from a given study. And that one sentence here would really be, we will see that there's a significant role for warping in really dictating the nature of some of the conclusions in each of these areas. So as we'll go through it, we'll see that the fact that not only when you turn on fluxes do you get a metric that's conformally calabi-Yau, but that back reacts on the metric on the moduli space, which gives it a warp-induced form as well, which will have a pretty big impact on the nature of the solutions that we find. Okay, so on to some of the standard lore on 2B flux compactifications. You can begin the story a long time ago when Candelas and collaborators showed us that if you're trying to analyze some of the mathematics and physics of calabi-Yau spaces, the real anchor, the real tool to have at your disposal is an understanding of the periods, that is the integrals of the holomorphic 3 form over a basis of 3 cycles in that calabi-Yau, and understanding how these periods vary as a function of position on the moduli space is a vital tool to be able to do analysis. Now, to actually do these calculations, they can be a little bit involved if you try to do them by brute force methods. I think the most economical approach is one that we focused on some time ago, to use these major G functions, which are solutions to these hypergeometric differential equations that have within them all of the machinery necessary to do the appropriate branch cuts and analytic continuations, and that'll be the approach that I'll follow here today. The one thing to bear in mind is that these equations solve in a particular basis that isn't necessarily the one of interest to us, which is the symplectic basis. So oftentimes we'll have to find the linear transformation between the two, but again, these solutions come equipped with a very simple and systematic approach for doing so, so we can be very explicit in these calculations. Now, once you have that data at your disposal, you can then go further and start to think about the physics of the situation. As we all know from the Gucko-Vafa-Witten superpotential that emerges in this context, if you turn on a certain amount of background flux, given an understanding of the periods, you can calculate the superpotential in the manner that we are by now all familiar with tau being the axiodilaton field. And I'll call this combination A plus B tau. This is a combination that will come up frequently in some of the calculations that we'll come to in a moment. Superpotential is, of course, one important part of the story, but we also need the Kähler potential, and that, too, for, say, the complex structure part of the moduli comes as well from an understanding of the periods. So if Q is the intersection matrix on these fellows over here, then that gives us enough information once we have the periods to calculate the Kähler potential for the complex structure moduli, and taking the standard form for the axiodilaton and the Kähler degrees of freedom, which I won't focus upon really at all in the discussion here today, we then have enough information to calculate the scalar potential of the theory using the standard form. And once we have that, we're off and running, and we can start to do some explicit calculations to locate vacua in the moduli space. Now, in doing so, there are two major approaches that people have followed. The first is to take a more statistical approach, which was pioneered by these authors, And the second approach, which I'll come to in a moment, is to actually drill down and find some explicit vacua, not in a statistical distributive sense, but ones that we can actually do some concrete calculations with. I will be focusing more on the second approach than the first, but let me just make one remark here that presages the main message, the role of warping, because we'll see that taking account of warping changes some of the conclusions that one otherwise would come to. So some time ago, these authors came to the conclusion that the density of the vacuum in the moduli space is given by this formula. Basically, it's the first Chern class of the moduli space. And using that, you can do some nice calculations, both from a theoretical expression as well as checking it, as these authors did, by explicitly finding vacua, of what the count of vacua on the moduli space looks like. So this is going way down, in particular, near the conifold point, which will play a significant role in what I'm talking about in a moment, special point in the moduli space. So way down near the conifold point and integrating out, this is how the count of vacua looks. And this familiar plot showing the accumulation of these vacua near the origin, in these coordinates, that is, the conifold point. Now, the thing to bear in mind is that, as I mentioned, warping impacts the near conifold behavior, as was pointed out by a number of authors. I'll be explicit about this in a moment, but let me just give the rough feel for it in this particular example first. So near the conifold, if this variable c is the variable whose value 0 is the conifold location, if you are looking in the non-warped version of the story, this is the kind of equation that you need to solve to find the vacua. And here you see if A and B differ by a couple orders of magnitude, because of the logarithm, there's an exponential dependence on that ratio, which is what gives us vacua that go extraordinarily close to the conifold, as we see over here. If you take warping into account, again, as I'll mention more explicitly, the form that we have over here is modified by a power law, where this coefficient c depends upon the volume of the Calabi-Yau. At large volume, this guy goes to 0, so the usual thought is, well, if we're working at large volume, we can forget about it. But of course, for any finite volume, there's a small enough value of c where this thing will matter, which means that rather than there being an exponential dependence, it becomes a power law one. So taking warping into account changes this picture in the manner that indicated here. The vacua basically get pushed out from the conifold in the manner that that graph indicates. Or if you look at a corresponding picture here, this is one little slice of the moduli space away from the conifold point, and you see, as a function of the value of this parameter c, as that parameter, let me just quickly show that again. So as that parameter gets bigger, the vacua get pushed out. So if you're standing at some distance away, you'll see the vacua rush by you, a wind of vacua, if you will, which are no longer clustered near the conifold point because of the warping. So that's one example of where warping makes a difference. But now let me focus upon the main work that I'd like to describe, which is to not look at the vacua in a statistical sense, but actually look at some concrete ones. And the ones that I'll focus upon are ones that were really brought to the attention by these authors who really pioneered this idea a little while ago, which is to look at vacua which are related by monodromy transformations on the moduli space. So as I think most everyone is familiar, but just to be complete, in the moduli space, if you're looking at a one-parameter Calabi-Yau space, there are a number of distinguished points, which can be labeled 0, infinity, and 1. 0 being the large complex structure point, z equal infinity being the Gepner or Landau-Ginzburg point, z equal 1 being the conifold point that I was mentioning just a moment ago. And the important fact is that if you undertake any non-trivial loops around these points, you find that the cycles do not come back to themselves in a trivial way. Instead, the cycles come back after being rotated by a particular transformation that I'll call T, the monodromy matrix. Now, what that means is the potential and the superpotential themselves are also modified if you take that kind of journey in the moduli space. In particular, if you look at the form for the superpotential, that comes from the fluxes that you turn on, it will receive that transformation on the period matrix, the period vector, I should say, by the monodromy matrix. And there are a couple of ways of thinking about this. In many ways, the most fruitful is to imagine that you're keeping the periods fixed, but you're simply changing the fluxes by this vector. So in the moduli space, you're going along some loop, and as you return back to your starting point, the fluxes have taken a jump given by the calculable monodromy matrix. Now, the reason why finding vacua that are related by these transformations is particularly interesting is the following. If someone hands you distinct values for fluxes that aren't obviously related, certainly not by this kind of transformation, you'd have two flux potentials, but it's not obvious how you stitch them together in order to have one potential that will allow you to talk about, say, tunneling in that particular setup. If the vacua are connected in this way, this gives us a recipe for joining the potential across vacua which have distinct values. And in that way, we can then look at two vacua which have different flux vectors and really have a single potential that spans across them, allowing us to do the standard kind of analysis, tunneling from one to the other. So that sets us up for a two-step procedure where what we need to do is minimize the potential first, say, as a function of the axiodilaton system, which you can do quite explicitly because it just gives you effectively a quadratic equation in the axiodilaton as a function of the fluxes. So here's A and B from the flux potential that I had before. So you can solve for the axiodilaton in that way, plug it back in to the potential, and then minimize the potential as a function of the complex structure moduli. That's something, of course, that you have to do generally numerically because it's too complicated to deal with otherwise, but it's something that is eminently tractable. So along those lines, let's look at a couple of concrete examples. Sticking with one parameter Calabi-Yau's, there are 13 Calabi-Yau's with one parameter that can be realized as complete intersections in projective or weighted projective space. And taking the mirrors of these, we'll be dealing with examples that have one complex structure parameter. The simplest and most familiar, of course, is the quintic in CP4. And here are some concrete examples. Danielson and company were first to write these down, where we have collections of flux vectors, F flux and H flux. These guys are all related by monodromy transformations. Here's the monodromy matrix if you're taking a path around the conifold point. It just takes this last entry over here and subtracts it if you're looking at the inverse from the first, so that 2 goes to 1 goes to 0. So these are 3 distinct flux vacua. Here are their locations in the moduli space, and they are all related, which allows us to construct a form for the potential that connects them in a continuous manner. So here's one of those vacua, the other, and there's this spiral staircase for the potential that allows you to connect one to the other. If you unwrap that and plot it in this way as a contour plot, then you see quite directly that you have a potential that spans all these 3 vacua, this guy, and this guy, and you could imagine trying to do, as we will in a moment, try to find the Como de Luce instanton that would take you from one to another, so you could actually realize that tunneling picture that I showed in the early part of the talk. Now that is for the quintic, just to show that this stuff is quite general. Just for argument's sake, if you look at model number 8, which is the quadratic and quartic in P5, again, a collection of flux vacua all related by monodromy transformations around the conifold point in that example. And again, I've only shown 2 of the vacua, but you can play the same game as we did on the quintic. And just to finish up these examples, model number 12 over here, 2 quartics in this particular weighted projective space. Again, you can find flux vacua where, again, the locations differ slightly by virtue of these transformations from sheet to sheet. The value of the minimum differs a little bit, but these are all connected by these monodromy transformations. Now, those examples were all non-supersymmetric vacua, where you had spontaneous breaking coming from the F-term contributions from the derivatives of the superpotential. You can also find supersymmetric vacua in much the same way. You can actually follow these chains all the way down until the value of the potential drops to 0, or you can simply work with the equations that directly enforce that the covariant derivatives of the superpotential vanish. And if you do that in models 1, 8, 12, and 14, just to give you some examples, you can find a collection of supersymmetric vacua all connected by monodromy transformations, all with different flux vectors. Over here, each of these has the same Ramon-Ramon flux, but they have these different guys over here. So if you then put these guys together into some little plots, the upshot is that we have chains of vacua that are just generated by these monodromy transformations, setting us up to try to do some analysis on them. And again, you can unroll the potential as well. The only difference between this case and the previous is that these guys are now down at 0, and when we consider the tunnelings between them, we're really considering domain walls between these supersymmetric minima. Okay, so without specification of the kinds of vacua that we'll be focusing our attention on, we can begin to think about the transitions from one to the other. And this was really first initiated, this kind of study was initiated by Johnson and Larforce. In their work, they identified and articulated some reasonable features that a tunneling trajectory would have in the landscape from one of these flux vacua to another by looking at the flux potential, seeing that there are certain places where there are ridges and saddle points, and very naturally suggesting that the bounce solution would follow the ridge and pass through the saddle point in a way that makes good intuitive sense. But the thing, of course, that you have to bear in mind here is that the goal of finding these tunneling solutions is complicated by the fact that we're dealing with an example where you've got highly non-trivial kinetic terms, because the metric on the moduli space is highly non-trivial. We're also dealing with a multi-field problem, which makes the standard shooting method quite awkward. In the standard shooting method, of course, you vary the initial starting point for the bounce solution, and you can overshoot or you can undershoot, and by continuity, as the classic argument goes, you're going to wind up reaching the desired turning point. But if you're dealing with a multi-field case, it's not a matter of just overshooting or undershooting. You can be going off in all sorts of different directions in the space of fields, so there's no comparable approach that is as effective as in the one field case. And this suggests to us to take a different approach to finding these instanton solutions, or domain wall solutions as the case may be. Rather than trying to shoot to find the solution, use a relaxation method. And the idea here is just choose any, hopefully close, initial seed domain wall profile, if I now focus my attention on the supersymmetric case. From that seed domain wall profile, find some physical quantity whose dynamical relaxation to its minimum will relax, will shift the initial seed trajectory to a static interpolating solution. So you start with some seed, you put in some, if you will, fake dynamics, allow the dynamics, hopefully if you've set it up correctly over time, to force your seed solution into the actual solution of interest, either the tunneling solution or the domain wall solution. So to put that into practice, it's useful to note that if you're looking at the domain wall solution, say between two of these supersymmetric flux vacua, you can reframe the equations as ones which are really seeking a minimization of the domain wall tension, which if the vacuum that you start with has, say, potential V1, this is the kind of quantity that you're trying to minimize, where phi is the field whose value is changing across the domain wall. To minimize that, the standard equations that we can derive from that. And now, in keeping with this relaxation philosophy, the idea would be to introduce some dynamics into the system. So rather than thinking about this field only as a function of x, say the direction orthogonal to the domain wall, imagine that it's also a function of t. put some time dependence into the system, note that you, in this kind of circumstance, will have a conserved energy associated with this particular set of equations. And in order to have relaxation, add a damping term. So if you add basically a friction term to these equations, the idea would be start with some seed. With this friction term, just allow it to run as a function of t, allow it to relax to the minimum, which will minimize the domain wall tension, and that's the way you can find solutions to the equations. Now, I'd like to do is apply that general idea to the case of interest here, which is our system with 4 real fields. So we've got our two real fields associated with the complex structure moduli Z, and we've got our 2 real fields associated with the axiodilaton system. And what we'll do is focus our attention on the conifold region, and I'll parameterize that in the following way. So z equals 1, and these coordinates is the conifold. I'll denote the variable that's the distance, the difference between z and 1, r e to the I theta, and I'll just write tau as u plus iv. And if I then write down the 1 plus 1 dimensional equations of motion that follow from this action, writing the Kähler potential as this guy f, those are the equations that we would like to solve. Those are the equations that we'd like to dynamically relax into a domain wall solution between distinct flux vacua, using this potential that we've glued together by virtue of the vacua being related by monodromy transformations. So we can set that up in the following way. If I denote these 4 real fields by this field vector phi, then I'm choosing boundary conditions off at minus infinity in space to be one of the flux vacua, boundary conditions at plus infinity to be the other flux vacua, and then I want to put in some seed solution as my initial trajectory. Again, just as in the general case, write down the conserved energy associated with that. Notice that by putting in a damping term, I can relax this solution that I start with into the minimum that we have over here, which will be the desired domain wall connecting these vacua. And if, at the end of the day, of course, we should check for the robustness of our solutions, that if you change your initial seed function, you don't want your result to change, and also to make certain that you've really reached the static solution. All of those checks we, of course, will do. Okay, so let's look at a concrete case of this, and I'll use the simplest example, which is on the mirror quintic. 2 of those flux vacua that I showed you in those tables earlier, which are supersymmetric solutions to the equations of motion. The specific data for these examples will be this. So here is the flux for the left vacuum state. This is the flux for the right one. Here's the position on the moduli space of the left, position on the right. And if I write these in my 4 real field formation, these are the data that describe those 2 points. Okay, so to follow the prescription, what I want to do is put in some seed trajectory, and I'll just put the simplest things that you could really imagine. Basically, a nice smooth trajectory that takes us from our initial point to our final point, both in theta and in r. And I realized I didn't correct a typo in this. This should be r2. That should be an x1. Sorry, but you get the basic idea. It's just its initial seed trajectory connecting the initial to the final point. And the analysis that we'll do, I'll do it in 2 steps for reasons that will become clear in a moment. So I'll start in what I'll call the far field region, which is a distance greater than 0.1 from the conifold point. And if I put in my seed trajectory, which are the black curves, both in r and in theta, and I start allowing the equations to relax, what we found is that the solution begins to relax toward r equal to 0, namely toward the conifold point. And if I just show you that dynamically here, this is what you find. The solutions just begin to relax toward r equal to 0, in this picture, that's the line at the bottom. This place, it's right down there in the middle. This is our theta coordinates. This is the unrolled coordinates. Now, the reason why I stress doing it in two phases is because, thank you, as I relax the solution, we find ever closer, we're driven ever closer to the conifold point. Now, the convergent properties of these major functions are such that as you get closer and closer to the conifold point, the convergence is ever more difficult and ever slower. So you need to switch over from doing it purely numerically in terms of those major functions into an understanding in a more analytic way of what's happening near the conifold. And thankfully, that's something that we know how to do quite well because we understand the nature of the metric on the moduli space in the vicinity of the conifold well. And let me just describe that to you and describe also the important effect of warping, which comes into the story over here. So the metric in the 10-dimensional spacetime takes the familiar warped form. And let me just ignore the warping for half a second and talk about the moduli space metric, and then I'll put in the warped deformed moduli space metric that's a function of A in just a moment. So the usual story is we start with the Kähler potential, and if we are looking in the vicinity of the conifold point, that's the point where one of the three cycles, call it A, that will be actually which will be the number 3 in this general notation. This cycle is going to 0 at the conifold point, so this is a regular function. C goes to 0 there. The dual cycle B, the one that intersects A, has a logarithmic dependence because as B is transported around A, it picks up a copy of A, as is well known just from the geometry of the situation. So we understand how those periods behave in the vicinity of the conifold quite well, allowing us to get a nice analytic expression for the nature of the Kähler potential near the conifold point in the moduli space. And again, in the non-warp case, this gives us our familiar logarithmic divergence associated with the metric, so the two derivatives of this guy on the moduli space. Now, how does the warp change this? Well, it was pointed out by these authors that you can describe the effect of the warp, the induced effect on the moduli space metric, by changing the form for the Kähler potential in this manner that I find here. So what that means is we should go back up to this expression over here, get rid of that old one, and put in the new one. And if you put in the new one and go through the same analysis, there is an additional term that arises when you do the analysis, the mathematical analysis carefully, that goes like a power law c to the 4/3. This is the same power law that came in when I was discussing the distribution of vacua a little while ago. This fellow, of course, dominates as c gets small. C2 itself is a function that drops as a function of the volume of the Calabi-Yau. So again, at very large volume of Calabi-Yau, this thing goes to 0, which is why people typically ignore it. But if you find, as we are, that the dynamical relaxation is driving the solution to the equations toward ever smaller values of c, at some point this is going to kick in. You can't ignore it. You have to take it into account. And in fact, for us, that's quite important because without it, the equations were not stabilizing. They were not becoming dynamically stable. When you put them in, as I'll now note, they do become stable. So as far as the potential goes, if you put in these modifications, this is the form of the potential in the vicinity of the conifold point. Again, c equal to 0 takes you to the conifold. And with that in hand, we can find the explicit form for the coefficients in the case of the example I was describing before. So for the mirror quintic with this particular flux vectors, these are the values of the coefficients that we have in this expression here. And using that, we can then go back and solve the equations. And it sort of went by a little bit fast. But what's happening here, I think if I can quickly go back to that picture. What's happening here is the solution is being driven right down near towards the conifold. But now we have analytic control over what's happening down there. So this actually is the solution. So if I just show you this is showing it as in a graph where we have the potential behind the curve as well. So again, this is the seed that comes from the far field region. This is our far field solution, which we then plug into this second phase, which gets us to our near-field solution, and putting them both together, we get a full solution. So the final profile, then, of the solutions looks like this. In the far-field region, we started with the black curve as our seed. We dynamically relaxed to the red. We then took the red as the input over here, so the red becomes the black. It's the input for the second phase. And here you see that we do get a nice, sharp domain wall solution between these two vacua, and the theta direction is also becoming nice and sharp as well. Now, I just have 5 minutes, great, so that's all I need. So just to give you a sense for then what's happening in these solutions, and just to call out in a more heuristic way the important influence of the warp factor. If we ignore the axiodilaton and just look at a very simple canonical form for a two-real field model moving in an inverse potential, well, in a simple example like this, the domain wall or the tunneling solutions would just be straight lines. There's nothing else that's happening in this case if the potential is, say, sufficiently mild to not really affect the results. But let's imagine the following constraint to mirror what we're actually doing in these Calabi-Yau examples. Assume that you have a multi-sheet potential with branch cuts from an initial point, I'll call it the conifold at r equal to 0, with the branches at these values of theta equal 2 pi n. Now note that the straight line that you get out of this very simple Lagrangian, if it's attempting to connect points whose angular separation is greater than pi, it's going to be obstructed because it's necessarily going to have to pass through this branch cut. So this would suggest that if you had a canonical kinetic term, you'd be limited, if this was the setup, to connecting points for which the angular separation was smaller than pi. If you have a kinetic term, however, which is non-trivial, say it goes like r to the 2 beta, then you can play the same game, do a little change of variables, and then in this form, you easily convince yourself that the angular separation goes like pi over beta plus 1. Now, in our case, beta was minus 2/3. That's the warp correction that we're finding for the metric on the moduli space, which tells us that delta theta max would be 3 pi, not pi. And that's important because if we go back to this example that we were looking at, if I can get the data for that back on the screen, I don't know where it is, but if you recall the actual, yeah, here it is. So if you look at the examples that we're looking at, connecting those supersymmetric vacua, the particular locations of these guys in the moduli space were indeed separated by more than 2 pi, between 2 pi and 3 pi, which means that without that warp factor, there would be no such solution connecting them. But with the warp factor, by this heuristic argument and by the explicit numerical calculation, there is a domain wall connecting them. We have explicitly found it. Now, the physical picture that you should have in mind for what's going on is, I think, pretty straightforward. If we again go back to the idea that we are minimizing the domain wall tension between the left and right vacua, well, what's happening is the following. So we're starting with some giving Calabi-Yau. The tunneling solution, or the domain wall solution, is taking us near the conifold where things are, a cycle is going real small, and then we're bouncing out and going to the other flux vacua at some point away from the conifold point. Now, if we plot here the three contributions, sigma 1, sigma 2, which are the contributions to the domain wall tension from this motion, and finally sigma m is the monodromy tension. This is where we're actually going around and forcing the cycles to come back to themselves by some non-trivial transformation. Three contributions to that energy. Well, you note that the prefactor goes to a constant near the conifold, whereas the metric goes like r to the minus 4/3. So this term and this term costs money, costs energy to go to ever smaller values of r. This term over here, however, because of this r, this guy wants the cycle to be small, and that makes good sense. If you're twisting around flux on a cycle, if that cycle is small, there's not going to be as big a cost in energy. So basically what we find is these three contributions kind of virialize in a way. When their contributions are more or less the same, that's where you find the static solution that emerges from the relaxation methods. So that's the physics of what's going on in these particular transitions. So what are the conclusions then? Well, I think the way to think about it is that these monodromy connected flux vacua provide a very useful arena for explicitly studying either domain wall connections between them, or you can also do tunnelings between those if you have some small breaking of the degeneracy. You'd have CDL instantons as opposed to domain walls. The multi-field and warping effects certainly complicate identifying the transitions. I wouldn't have thought that the transitions would naively have been driven close to the conifold in just looking at the potentials, but it's hard to see through the potentials when you have these complicating effects. And indeed, we find that the dynamics do drive the interpolating configurations near the conifold. And it's a kind of universal behavior that's controlled by the warping of the moduli space metrics. So what we find here would be basically true for any Calabi-Yau's where we're studying warped flux vacua in the vicinity of the conifold. It'd be very interesting to determine how general this is. What if you're talking about vacua which are not monodromy related? That was really a crutch, a tool that allowed us to use standard techniques and have a single potential that spanned both of the flux vacua. But presumably, there's nothing special about that technique, so the conclusions perhaps are quite general. That is, when you're looking at tunneling solutions or domain wall solutions connecting these various vacua, the conifold may be kind of an attractor that drives the instanton, drives the domain wall in the vicinity of that point. So the goal ultimately would be to view this as, again, one of the early steps to try to understand, the nature of the tunnelings in the landscape in a very explicit way. One day, hopefully, these kinds of ideas can be developed to the point when we can really do cosmology on the landscape and have some real sense about if this landscape picture is correct, what the nature of the distribution of the vacua, the nature of the distribution of these bubble universes would be. Thank you very much.
Yeah, so in the large flux region, one would expect the transitions to be given by 5 branes that wrap the various cycles. So I was wondering if your solution could be interpreted as a 5 brane that wraps the conifold.
Absolutely.
In a small cycle.
Yeah. So in the early slide, remember I was simply noting that if you do a monodromy transformation, you can either view it as a transformation on the cycles, or you can view it as a transformation on fluxes, and I was focusing more on transformation of the fluxes, and both of those pictures are complementary. But in that latter picture, you can certainly imagine that what's happening is a 5 brane is wrapping this guy over here, so you've got 2 dimensions giving us our domain wall, the 3 dimensions in there, and then that picture of it is just that 5 brane wants to wrap something small. And that's what drives it towards a small value of the cycle right near the conifold point.
But is the domain wall of the tension you find in the end equal to the
It's a good question. Yeah, it's a good question. And it's a calculation that we haven't really completely sorted out. So it is a natural one to ask, but I don't know. It should be.
Could you comment on the validity of the supergravity approximation for this?
Well, that's always a bit of a headache. We're certainly ensuring that the only solutions we're looking at are where G string is small. So there's all sorts of solutions where it would be big. We just throw all those away. I have most confidence, of course, in the ones that are supersymmetric. So the domain wall solutions are the ones that I would have most confidence in. If you're actually applying this, which we haven't, but others have, to Coleman-de Lucia instanton solutions between the non-supersymmetric vacua, I think you run into the usual story. Do you trust these or not? If the fluxes are sufficiently small, if GS is sufficiently small, you hope that the existence of small expansion parameters is enough. But I don't really have anything more to say to give any greater confidence in that.
No
more questions. So let's have a break.